Have you ever wondered what it feels like when another star sends something our way? In this documentary, you will uncover the true story of 3I Atlas, an interstellar visitor that defied everything we thought we knew about the universe. You'll hear how it breathed, fractured, and disappeared, yet left a message written in light. So sit back, relax. You've come to the right place. And before we begin, subscribe to Whisper Science and tell us in the comments from which country you're watching the universe tonight.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.
Have you ever wondered what silence sounds like when it starts to move? Out in the black, where sunlight is only a whisper and every rock drifts through a cathedral of emptiness, something began to exhale. It was faint at first, a vapor shimmer that no telescope expected to see. Astronomers studying the dark between Mars and Jupiter caught the trace in ultraviolet light, a fragile halo that shouldn't have existed. A comet, catalogued as 3I Atlas, was breathing water into space. Not droplets, not a trickle, but torrents. 40 kilograms every second, evaporating from a frozen body so distant from the sun that ice should have slept unmoving for millennia. Out there, sunlight is too weak to melt anything. Temperatures fall below 160 degrees below zero. Comets at that distance are corpses, silent, inert, fossils of the early cosmos. Yet 3I Atlas was awake. At first, researchers thought it was a sensor artifact, a ghost in the detector. But data from SWIFT, the same spacecraft that hunts gamma-ray bursts, confirmed the impossible signature: hydroxyl, the torn remnant of water molecules split by solar radiation. Wherever hydroxyl glows, water has just died, and it was dying fast. That single signal meant the comet was streaming about 1.3 x 1027 molecules each second, enough to fill a swimming pool every few minutes, from a region where heat should not exist. What could drive such defiance of physics? Some whispered outgassing anomaly. Others dared internal heat source. Yet the numbers refused to settle. If 3I Atlas truly came from another star, an interstellar migrant like Oumuamua and Borisov before it, then its chemistry was born under a different sun, in a disk with alien ratios of ice metal and radiation. Maybe in that distant system, water was never the same kind of solid. Maybe its crystal lattice carried impurities that lowered its sublimation point, allowing vapor to escape where ours would stay locked. For days, telescopes pointed and recalibrated. The comet's coma, the glowing shroud of gas, thickened visibly. Through ultraviolet filters, it looked alive, pulsing faintly, as though some slow heartbeat guided each plume. No one could explain the rhythm, and so the theories multiplied. Could internal radioactivity from isotopes long decayed in our system still simmer inside? Could cosmic ray bombardment fracture the surface, exposing pockets of volatile material that erupt once light touches them? Every hypothesis felt incomplete, like describing a storm by counting raindrops. The deeper question haunted them all. If 3I Atlas breaks our rules, then whose rules is it following? Somewhere around some other star, chemistry wrote a different grammar, and this comet is speaking it. Ground observatories joined the hunt. The VLT in Chile, the Keck pair in Hawaii, the ultraviolet eyes of Hubble. Each saw layers of contradiction. Dust jets emerged from shadows where sunlight barely reached. The tail curved against the solar wind, hinting at magnetic interference. Within weeks, the object's apparent brightness had quadrupled, not because it moved closer, but because it grew more active, as if the darkness itself nourished it. Astronomers, usually fluent in numbers, began to sound like poets. They described 3I Atlas as awake, listening, even breathing. The language of data gave way to metaphors because equations alone could not capture what they saw. And perhaps that's the point. Science begins where words fail and curiosity refuses to stop. By late observation runs, one pattern stood out. The emission peaks pulsed every 19 hours, a rotation period perhaps, or something stranger. Every 19 hours, the spectrum brightened in hydroxyl and then faded, like a lighthouse turning through fog. That rhythm let them map the comet's spin, but it also raised an eerie implication. Inside that tumbling nucleus, pockets of volatile ice might be arranged in stripes or layers, releasing bursts only when sunlight swept across specific regions. In that sense, 3I Atlas wasn't random. It was orchestrated, not by intention, but by structure, by geometry fossilized billions of years ago around another star. And still the riddle deepened. Instruments caught traces of cyanide, CN radicals that glow green, emerging hours after the water peaks. Then came nickel lines, bright and sharp, but curiously alone. Iron, which should accompany nickel everywhere, was absent or drowned in noise. Nickel without iron, a metallic solitude that should not exist. That detail would explode into its own mystery later. For now, it was simply one more crack in the mirror of our expectations. Each new observation forced humanity to confront how provincial its science can be. We model the universe with what we know, but we know only one planetary system. 3. I Atlas is the first clear reminder that the cosmos is under no obligation to resemble us. Somewhere, perhaps 10,000 light-years away, a star once burned with a different color, surrounded by a disk where nickel was plentiful, where water behaved oddly, where ice stored heat like memory. When that system tore itself apart, through gravitational chaos or stellar death, fragments were flung into the interstellar void. One of those fragments drifted for eons until it crossed our path, carrying the signature of its birthplace embedded in crystal and metal. That fragment is here now, tracing a brief, luminous arc through our solar system, challenging every equation we thought was settled. As data poured in, astronomers noticed something unsettling. The water release was increasing as the comet receded slightly from the sun, not decreasing. By all logic, activity should fade with distance. Yet the opposite occurred. Perhaps the surface was cracking open from internal pressure, exposing fresh reservoirs. Perhaps thermal inertia, heat lagging inside the nucleus, drove delayed eruptions. Or perhaps, as one researcher half joked in a conference hallway, the thing just likes the dark. No one laughed. Because deep down they all sensed it, that rare electric feeling that comes when the universe reminds us it still has secrets. 3. I. Atlas wasn't just a comet. It was a question wrapped in ice. A question that whispered, "How much do you really know about the rules you live by?" And as it turned its faint emerald halo toward the inner planets, astronomers began preparing for what came next. The phase when metals, gases, and light would tell stories never written in our textbooks. They didn't know it yet, but 3I Atlas was about to rewrite more than chemistry. It would force us to reconsider where we came from and what else might be out there, breathing quietly in the dark. The first time the spectrum came through from the very large telescope in Chile, no one in the control room spoke. The lines were too clean, too bright, razor-thin bands of nickel shimmering in the green-blue range like threads of molten wire stretched across the void. Everyone expected to see iron paired with it. That's the rule written into every comet we've ever known. Nickel and iron are twins, forged together in the bellies of stars and released in the same supernova breath. Yet 3I Atlas glowed with only one of them. Nickel stood alone, gleaming defiantly while iron hid somewhere below the threshold of detection. To understand why this matters, you have to picture what metals mean in space. Their memory. Every atom heavier than helium was born in a furnace, in a dying star S-core, or in its explosive death. The ratio of nickel to iron tells astronomers which kind of supernova seeded the gas that became a system. It's a chemical signature, a cosmic fingerprint, and 3I Atlas carried a fingerprint no one could match. At first they blamed calibration errors, maybe a thermal ghost in the spectrograph, a bit of light scattering off a mirror. But after 3 independent observatories confirmed the same pattern, nickel blazing, iron whispering, denial turned to calculation. Could nickel be trapped in a volatile compound, released earlier than iron as the comet warmed? Some metals can form organometallic molecules, fragile cages of carbon monoxide and metal atoms. If the environment where this comet was born was rich in carbon monoxide, those molecules could evaporate at surprisingly low temperatures. Nickel would escape easily, leaving iron behind. That's elegant on paper, but the numbers fought back. To produce the observed intensity, half a ton of nickel would need to vaporize every day. For an object scarcely 10 kilometers across, that's unsustainable unless nickel exists everywhere in its outer crust. And that possibility, an entire surface laced with metallic veins, hints at a birthplace unlike any we know. Perhaps its parent star formed in a region where the yields of supernovae were skewed. The thick disk of the Milky Way, older, poorer in iron, still bears the scars of early cosmic alchemy. Maybe 3I Atlas was born there, billions of years before the Sun, in a nebula where nickel had the upper hand. If that's true, this small wandering comet is older than our oceans, older than the Earth itself. A fragment of chemistry from a time when the galaxy was young and wild. Yet even that theory leaves an itch unscratched. For the nickel lines to flare so vividly, the atoms must be free, stripped from dust grains, excited by sunlight or solar wind collisions. That requires constant replenishment. Something inside the comet must be feeding the glow, releasing fresh material like breath from a wound that never closes. The data points towards cyclic heating. Every 19-hour rotation exposes a different face to sunlight. Imagine fissures lined with metallic frost, narrow vents that open and close as the surface expands and contracts. When a sunlit side faces Earth, those vents exhale, flooding the coma with nickel atoms that catch the light like tiny mirrors. When the comet turns away, the emission fades. A heartbeat again, this time not of water but of metal. Observers started calling it the singing stone. The nickname stuck because the emission lines looked like notes on a staff, each observation a measure in a song we didn't compose. Somewhere between art and data, scientists began to sense intention, not consciousness, but patterns so intricate it felt alive. And still, the question of the missing iron refused to die. If iron truly isn't there, then the separation must have happened at birth. Maybe during condensation, nickel hitched itself to volatile ice, while iron bonded with refractory silicates. In the swirling protoplanetary disk of another star, that subtle chemical fork could have rewritten the comet's destiny. Billions of years later, those choices still echo across light years, reaching our telescopes as a faint green hum. A few dared a wilder idea, that cosmic rays over eons transmuted the outer layers, shattering iron bonds and leaving nickel intact. Space is not gentle. High-energy particles carve new chemistry into old matter. Over 1 billion years drifting through interstellar space, every square centimeter of the comet air skin would have endured quadrillions of impacts, enough to alter minerals, to redden dust, to turn ordinary rock into something half alien. Maybe that's why it glows so strangely when the sun finally touches it. The scars themselves shine. As debates raged across conferences, one theme returned again and again: context. We have only 3 interstellar visitors on record: Oumuamua, Borisov, and now 3I Cam, Atlas. 3 data points in a galactic ocean. 2 of them already contradict each other. Perhaps the universe isn't broken. Perhaps our sample is too small. Maybe nickel without iron is common out there, and we just never looked far enough to see it. That realization sent a quiet thrill through the community. Every oddity in 3I Atlas isn't a mistake to fix. It's a message to translate. Each deviation whispers that the chemistry of planets, of oceans, of life itself might take endless forms depending on the furnace that forged the raw materials. Somewhere under different suns, there could be worlds built from such unbalanced recipes, seas glimmering with metallic salts, mountains veined with nickel ice, skies tinted green by vapor we'd never breathe. Back on Earth, lab spectroscopists began recreating the comet's signature. They cooled metal-rich powders in vacuum chambers, bathed them in ultraviolet lamps, and waited for the telltale lines to appear. Some came close. None matched perfectly. The ratio remained off, as though the universe guarded its formula behind one more layer of mystery. Meanwhile, the comet kept rotating, its nickel heart beating under starlight, and astronomers, exhausted yet spellbound, understood that this wasn't the end of the riddle, merely its metallic overture. Whatever force could unpair iron from nickel might soon unpair reason from expectation. Because 3I Atlas was only beginning to show what else it could become. It began with a flicker, the kind that hides inside graphs, an upward bend on a brightness curve that shouldn't have existed yet. Comets, by the laws we know, awaken slowly. As they fall toward the sun, light warms the surface, ice sublimates, dust lifts, tails bloom. Predictable, gentle, mathematical. But 3I Atlas refused calm. Its brightness leapt like a living thing startled from sleep. Night after night, telescopes from Chile to Hawaii watched the numbers surge. The slope was wrong, too steep, too early. At 3.5 astronomical units from the sun, where even sunlight seems tired, the comet was exploding with activity. And then, almost theatrically, its color shifted. The neutral gray of rock turned to green, a soft, eerie luminescence that bled outward like a bioluminescent tide. Photographs caught it first. Astronomers checking their calibration thought the filters were contaminated, but spectroscopy told the truth. Cyanide and nickel, both radiating fiercely in the green wavelengths, both rising together as the object drew closer to the sun. Every model failed. If sublimation were purely thermal, brightness should have increased smoothly. Twice as close means 4 times as bright. That's geometry. Yet 3I Atlas brightened faster than that, exponentially, as though new engines ignited within it. The term the scientists used sounded mechanical: switch-on behavior. It describes a process that waits, locked behind a threshold, until heat or light flips an invisible switch. And then the comet doesn't just respond, it transforms. The first switch was water. At a distance where normal comets are still silent, 3I Atlas was already venting 40 kilograms per second. Then came cyanide, the green ghost. Then nickel, the metal that should have slept. Each element seemed tied to a different trigger temperature, a different depth inside the nucleus. Imagine layers of ancient ice stacked like pages in a book. each page written in a different language of chemistry. As the sun's light deepened, one page after another began to read itself aloud. Some scientists proposed extended icy grains, tiny fragments lifted from the surface that drift outward before they warm enough to sublimate. Each grain becomes a miniature comet, creating a cloud of secondary activity that amplifies the overall glow. Others suspected fracturing. Comets are fragile, riddled with pores and veins. When heat spreads unevenly, one side expands while the other stays frozen. Stress builds. Eventually, something cracks. When it does, buried material once shielded from sunlight meets the vacuum, releasing gas in sudden, furious breaths. 3. Atlas, by that logic, wasn't waking gently. It was tearing itself open, layer by layer. Images taken weeks apart confirmed it. Jets appeared where none had been before, new vents, new plumes. Dust patterns shifted daily, as if the nucleus were rearranging its own geography. Its rotation may even have changed, torque from escaping gas nudging its spin into new rhythms. For a few observers, the parallels with life were irresistible. Birth, growth, decay, thermodynamics playing dress-up as biology. The comet seemed to pulse with intent. In late-night emails between observatories, scientists half-joked about heartbeat sequences and breathing cycles, but the humor carried a thin edge of awe. Because every time 3I Atlas broke a rule, it forced them to rewrite what rule even meant. High-resolution photometry revealed subtle color variations within the coma. Green cores surrounded by pale cyan halos. That layering hinted at chemical segregation. The materials escaping weren't mixing evenly, but forming zones, each dominated by different volatiles. If one could trace those zones back to the nucleus, they might map its internal architecture, perhaps even infer how it formed billions of years ago around a star whose name we'll never know. There was also light scattered from micron-sized dust grains, tiny mirrors reflecting solar rays with surprising polarization. That detail suggested the grains weren't random, but elongated, maybe needle-like crystals formed under slow freezing conditions. Such shapes don't form easily in quick, violent condensation. They need time, calm, and low turbulence, which means the birthplace of 3I Atlas might have been a region of exquisite stillness, a nursery where ices grew undisturbed for ages before being ejected into chaos. The comet, in short, was a paradox, born of serenity behaving like a storm. Then came the outbursts, brief surges of light that spiked and faded within hours. Amateur astronomers, monitoring from backyards with modest telescopes, captured the flashes and uploaded them to community networks. One by one, they plotted the events, and a pattern emerged, bursts recurring roughly every 3 rotations. Something cyclic, something deep. The nucleus was behaving like a breathing lung, exhaling volatile gases through fractures that opened and closed with thermal tension. Every third turn, a deeper seam released its trapped reservoir. It was beautiful and terrifying. If the pressure kept building, the entire nucleus could fragment. Many comets end that way, splitting into shards, each a glowing ember that fades into dust. Would 3I Atlas survive its own awakening? No one knew. The tension between fragility and endurance became part of its legend. When spectra from the Hubble Space Telescope arrived, they revealed faint ultraviolet lines corresponding to excited oxygen. That meant water vapor was still being ripped apart by sunlight, far from the nucleus, sustaining a vast invisible envelope around the comet. It wasn't just active, it was saturating space with fragments of its own chemistry, building an expanding sphere of altered vacuum, tens of thousands of kilometers wide. Within that sphere, ionized particles danced to the solar wind. Magnetic measurements detected weak but persistent fluctuations, as if the comet were developing its own temporary magnetosphere. Not strong enough to shield anything, but enough to organize chaos, a miniature world, self-contained and fleeting, born from nothing more than ice, light, and motion. Human eyes, accustomed to lifeless rock and gas, found poetry in that fragility. A body older than the sun, crossing our sky for a heartbeat of cosmic time, shaping its own weather as it died. For those studying it, every data point carried both wonder and warning. If one interstellar object could act like this, how many others slip past unseen, writing chemical alphabets we'll never read? How many stellar histories drift silently between suns, erasing themselves before we can learn their story? As the comet brightened, so did the sense of anticipation. The next threshold, nickel saturation, was approaching. Models predicted that once surface temperatures reached a certain point, metallic emissions would spike again, possibly revealing more exotic elements hidden beneath. And if that happened, the question of composition would no longer be academic. It would redefine what interstellar chemistry can be. The world watched numbers crawl across screens. Telescopes pivoted nightly. Every green pulse, every brightness flare, every shift in spectrum felt like listening to a heartbeat through the dark. 3I. Atlas wasn't supposed to be alive, but tell that to the silence now trembling around it. To know what something is, you have to know where it was born. Every comet, every grain of cosmic dust carries a trajectory, a curved sentence written in gravity's script. When astronomers finally plotted the orbit of 3I Atlas with enough precision, the line refused to close. It wasn't an ellipse, it was a hyperbola. That single shape said everything. This object didn't belong here. It came from outside the sun's dominion, from the cold, unlit gap between the stars. It was a visitor, not a citizen. They traced its path backward across the sky, searching through years of archived survey data. There it was, faint and unnoticed, hiding in frames taken months before anyone knew it mattered. Little more than a speck among millions. Each rediscovered image tightened the calculation, pulling the orbit farther and farther outward, until it escaped even the galaxy's gentle curve. Somewhere out there, between spiral arms, lay its beginning. That realization changes how you look at it. A comet isn't just ice and dust, it's a piece of someone else's history. To trace its motion backward is to travel through time, past the birth of our sun, past the assembly of our own planets, back into a cosmic nursery where the rules of chemistry were still being written. The data hinted that 3I Atlas didn't come from the galactic thin disk where our sun lives. Its inclination and velocity pointed to the thick disk, an older, puffier population of stars that orbit higher above and below the Milky Way's plane. Those stars are ancient, born when the galaxy itself was still young, when supernovae were rare and heavy elements were scarce. Fewer metals meant simpler chemistry. Planets there would have been rocky but lean, their crusts poor in iron and magnesium, their ices rich in carbon and nitrogen. If 3I Atlas came from that neighborhood, it is carrying samples from a time when the Milky Way was half its current age, a fossil of prehistory older than any stone on Earth. Imagine it, a star surrounded by a thin, cold disk of gas. Dust begins to clump, ice condenses, planetesimals collide. Within that chaos, small bodies form, each one a capsule of the local conditions. Some are flung inward, feeding the birth of planets. Others are hurled outward, beyond the system's gravitational reach. One of those castaways might be 3I Atlas, ejected at tens of kilometers per second, free forever, carrying the isotopic memory of its home star. That journey would have taken millions of years, millions spent drifting through the interstellar dark, where nothing warms and nothing cools because everything is already frozen. Cosmic rays etched scars into its surface, breaking bonds, creating new compounds unknown in our solar system. Hydrogen fused into defects inside its ice lattice, carbon chains mutated into tar-like substances. Each impact, each century of radiation, wrote another line into its long, silent autobiography. By the time it crossed paths with our sun, it wasn't the object that left its home. It was older, weathered, infused with cosmic history. The irony of discovery is that we always meet these travelers at the end of their stories, never the beginning. Astronomers, unwilling to leave the mystery unquantified, asked a harder question. Could they find its birthplace? Could a star be identified whose past trajectory once intersected this comet's outbound line? Using data from the Gaia Space Observatory, which tracks the motions of over 1 billion stars, they ran simulations, tracing orbits backward across galactic time. Thousands of potential crossings appeared, then fell away as uncertainties compounded. But a few persisted, slow-moving, metal-poor stars about 7 billion years old, wandering high above the galactic plane. None could be confirmed, but the pattern whispered truth. 3I Atlas likely formed in a stellar population older than the Sun by at least 2 billion years. That means its chemistry reflects a different era of the universe, when iron was rare, when carbon was abundant, when oxygen was a luxury. That might explain everything. The nickel without iron, the high carbon dioxide ratio, the persistence of cyanide. In an environment with fewer refractory elements, volatile compounds would dominate. Planets there might form with crusts of carbon glass and ices of nitrogen. Oceans, if they existed, would boil away under weak sunlight, leaving behind worlds of frost and shadow. And within those systems, comets like 3I Atlas would be their messengers, custodians of all that chemistry, waiting to be thrown into the dark. The idea haunted scientists. Somewhere out there, a solar system with a redder star, long gone cold, might have birthed this wanderer before the first humans even dreamed. That star might have died quietly, its planets consumed, its comets released like spores. We are now breathing the faint residue of one of those spores billions of years later. There's a romantic danger in thinking that way, an urge to anthropomorphize, to imagine intention. But what makes it compelling is precisely that there isn't any. The galaxy doesn't mean for us to find these things. We simply happen to live in a time when our telescopes are sharp enough to notice. Out of billions of frozen exiles drifting through space, one wandered close enough to be illuminated, and in its reflected light we caught a glimpse of our own ignorance. Even the orbit tells a story of violence. Its eccentricity is greater than 1, unbound. But its approach vector isn't random. It entered the solar system at a shallow angle relative to the ecliptic, as if grazing the edge of a planetary disk rather than piercing it. Some wonder whether gravitational tugs from stars in the galactic thick disk had slowly reshaped its path, bending it toward us over millions of years. Others think it was chance, pure and indifferent. Whatever the cause, the result is the same. A visitor crossing our sky for a brief moment, then leaving forever. We will not see it again. The sun's gravity cannot hold it. Its speed ensures escape. For us, 3I Atlas is a once-in-civilization encounter, a reminder that the universe is porous, its borders open. When the comet's light curve is plotted against time, its peak aligns eerily with its closest approach to the sun, perihelion. but its decline is slower, more graceful, as if reluctant to leave. In that fading glow lies the last whisper of its origin. The dust it leaves behind will continue to orbit the sun for centuries, small particles joining the zodiacal haze that paints our night sky. Each speck, when it burns in our atmosphere, will trace a microscopic flash of alien chemistry across our air, a final handshake between two star systems that never knew each other. For astronomers watching from observatories on cold mountain peaks, that thought brings an odd comfort. In the scale of cosmic time, we are also just visitors. Earth itself is an interstellar traveler, carrying fossils of stars that died before it existed. The comet merely reminds us of that truth. So when you look up tonight and see a faint streak of green light cutting across the darkness, remember, you're not just watching ice evaporate, you're watching the galaxy talk to itself, one fragment at a time. Every comet is a container, a sealed archive drifting through vacuum. Its ice and dust are not just debris, they're data, chemical stories frozen since the dawn of whatever world gave them birth. But 3. Atlas, this green, impossible wanderer, seemed to carry cargo stranger than most. Astronomers expected water. What they found was imbalance, an atmosphere made mostly of carbon dioxide, with only a whisper of H2O. In our solar system, that ratio is reversed. Here, water is the dominant volatile, carbon dioxide the supporting act. Out there, apparently, someone had switched the script. At first, instruments on Earth questioned themselves. Carbon dioxide is difficult to measure remotely. It hides in infrared, where Earth's own atmosphere glows. But orbital observatories confirmed the truth. 90, perhaps 95% of all gas streaming from the comet was carbon dioxide. Water made up only a trace. No comet born near our sun behaves that way. In our own system, such ratios don't occur even among Kuiper Belt bodies, those ancient residents of the outermost regions. The only explanation was origin. 3. Atlas had formed in a nursery where carbon was king and oxygen a rare currency, a region of chemical poverty unimaginable until now. Then came another surprise, the cyanide signature. CN molecules usually appear hand in hand with water because they sublimate at similar temperatures. Yet in 3I, Atlas, cyanide appeared late, as though locked behind a deeper layer. Something inside held it captive until the comet warmed beyond expectations. When it did, the release came not as a steady flow but a pulse, a chemical heartbeat adding to the comet's rhythm of outbursts. And beneath that cyanide glow was nickel, lonely, defiant nickel, still shining without iron. It wasn't just an absence anymore, it was an insistence. The data made it undeniable. This object's chemical proportions could not have been born under any star like ours. The mix was alien, older, colder, perhaps sculpted by radiation fields unlike the sun's, where ultraviolet light shaped molecules in slower, stranger ways. To scientists, this was thrilling. Each spectral line is a clue, each deviation a fragment of a puzzle spanning the galaxy. To everyone else, it was something simpler, proof that the universe still holds secrets no one can domesticate. But beyond chemistry lies imagination. Some asked a forbidden question. What if the cargo wasn't just inert molecules? What if it was potential? There's a theory, beautiful, controversial, impossible to prove, called panspermia. It suggests that life, or at least its raw ingredients, might travel between stars on objects like this. Not living cells, which radiation would destroy, but amino acids, nuclear bases, sugars, the precursors of biology. tucked safely inside ice and rock. Comets could be couriers of possibility, scattering the seeds of chemistry across light years, ready to germinate wherever they land. 3I at Atlas seemed to fit the profile disturbingly well. Water traces, complex organics, cyanide, all essentials for prebiotic chemistry. It was tempting, almost poetic, to imagine it as a messenger from a dead world, carrying fragments of chemistry that once tasted sunlight under another sky. But romance is not evidence. The harsh truth is that interstellar space is merciless. High-energy particles tear apart complex molecules over millions of years. Ultraviolet light cracks carbon chains. Whatever amino acids might have formed at birth would long ago have been reduced to dust. And yet, not everything dies completely. Beneath meters of shielding ice, some molecules could survive, stable, but sleeping, their bonds preserved by cold so perfect it borders on stasis, not alive, not conscious, but intact. If one of those fragments fell onto a young planet's ocean, it might join local chemistry, nudging evolution forward. Not the spark of life, but a whisper in its ear. When scientists talk about building blocks, they mean precisely that, the alphabet of atoms that life can rearrange. Hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, letters from which proteins and DNA can be written. Every comet, by existing, is a library of those letters. And 3I Atlas might carry an older dialect, one written before our alphabet existed. The dream of retrieving a sample haunted every researcher who looked at it. Imagine holding ice that formed around another star 7 billion years ago. Its isotopes could reveal how that star burned, how its radiation sculpted chemistry, how its planets lived and died. But interception is nearly impossible. Interstellar comets move fast, dozens of kilometers per second. By the time we notice them, they're already leaving. For 3I Atlas, it was too late. No probe could catch it. All we could do was watch as the gift passed by, unreachable. Still, even light is a sample. Spectroscopy is the art of listening to atoms sing. Each line in the spectrum is a vibration, a frequency unique to its element. From those songs, scientists reconstructed a symphony of alien chemistry: carbon monoxide, carbon dioxide, cyanide, traces of ammonia, maybe even formamide, a molecule that on Earth acts as a bridge between simple chemistry and biology. Nothing conclusive, nothing alive, but the right notes played in the right order. For the public, the idea of a living comet returned again, louder this time. Social networks filled with questions. Could it be carrying life? Could something be inside? Scientists replied carefully, no, not life, just chemistry. But even they couldn't suppress the thrill of saying the words, just chemistry, when that chemistry had traveled across the galaxy. There is something profound about that. The notion that elements forged in one sun's death could drift for eons, and then, for a moment, glow in the light of another. A comet like 3. Atlas is a bridge between times, between worlds, between versions of the Milky Way itself. It shows that nothing truly ends, it only changes location. In quiet moments, when observatory domes closed for the night and computers hummed with data, a few astronomers admitted the same secret thought, that watching the comet felt like reading a letter you didn't remember sending. Its chemistry mirrored ours in just enough ways to feel familiar, yet its accent was foreign. Maybe the galaxy is full of such letters, each one written in the language of atoms, waiting for someone to learn how to read them. When 3. Atlas finally begins its long outbound journey, most of its water and gas will be gone. The sun will strip it bare, leaving a dark core tumbling through the cold again. But inside that core, sealed away under crust and dust, the old molecules will persist. Proof that time doesn't erase, it archives. Every fragment of its vapor that escapes into the solar wind will scatter across millions of kilometers, thinning into nothing, yet still carrying fingerprints of an ancient star. Some atoms will end up embedded in Earth's atmosphere, some trapped in the magnetosphere, a few perhaps landing silently on the moon. The galaxy's circulation system will continue, stars exhaling, comets inhaling, the elements trading places like dancers. If you could compress all that motion into a single frame, you'd see that the Milky Way breathes. And comets like 3I Atlas are the breath itself. Every great cosmic discovery begins not with certainty, but with curiosity, and often not from the institutions we expect. 3I Atlas was first noticed by survey telescopes, but its real story unfolded because of the people who refused to stop looking once the professionals moved on. They were citizen scientists, amateur observers, students with borrowed equipment, programmers turning raw data into images at 3 in the morning. The kind of people who, when faced with a sky full of noise, somehow notice the one thing that doesn't fit. Astronomy has always relied on such eyes. Machines are tireless, but they lack intuition, the subtle human sense that whispers, "This is odd." It was that whisper that brought 3I Atlas back into focus after its initial classification. While algorithms filed it under ordinary long-period comet, a handful of volunteers on a public data project saw something else in the early images. A brightness curve too steep, a coma too broad for its distance. They flagged it for review, expecting maybe a calibration issue. Instead, they reopened one of the most fascinating mysteries of the decade. Those volunteers belonged to a distributed program called Atlas Watch, a network where public participants sift through terabytes of sky data searching for transient events. The software presents one frame after another, a star field, a patch of static, a flicker of motion. Most people scroll past hundreds of false positives, satellites, cosmic rays, camera ghosts. But sometimes, someone pauses. One user in Finland described it later. There was something alive in that image. The way the light spread felt wrong. So I clicked it. That click traveled across the network, summoning astronomers who verified the object's identity. Within days, professional telescopes pivoted toward it. The data flood began, and soon the words interstellar origin entered the conversation. Without that human hesitation, that refusal to scroll past the anomaly, the story of 3I Atlas might have vanished into digital background noise. Citizen science, for all its chaos, thrives on such moments. In 2019, volunteers had already proven their worth by discovering the first odd radio circles, enormous faint loops of radio emission floating like smoke rings around distant galaxies. Computers missed them because they weren't points or lines, but vast gradients, patterns that exist only when seen with a certain kind of patience. Humans caught them precisely because they didn't know what not to expect. The same thing happened here. The public caught an echo that code dismissed, and in doing so reminded the scientific world of an uncomfortable truth. Sometimes, discovery needs imperfection. Machines excel at repetition, but novelty hides in the noise, and only human curiosity loves noise enough to listen. As weeks passed, more amateurs joined in. Backyard astronomers, some with telescopes no larger than dinner plates, began recording the comet's movement. They coordinated through online forums, sharing data that professional teams later integrated into orbital solutions. That collaboration blurred the old boundaries between official and enthusiast. The cosmos doesn't care who holds the telescope. Light falls on everyone equally. For many of those volunteers, 3i Atlas became personal. They watched it nightly, adjusting focus, chasing its faint green glow as it climbed through constellations. One participant in Australia described the feeling as watching a stranger walk across your front yard, knowing he came from another country and will never return. Another compared it to whale song, brief, haunting, impossible to ignore once heard. But not all reactions were poetic. Some were suspicious. The very openness that made citizen science powerful also let misinformation creep in. On social media, fringe groups began claiming the comet's behavior proved hidden agendas, secret experiments, alien probes, government silence. A few even insisted the object was artificial. They shared manipulated images, exaggerated spectral data, and speculative diagrams that spread faster than any peer-reviewed paper could catch up. For the professionals, this was frustrating. For the amateurs, it was exhausting. They found themselves defending the science they loved from the same public enthusiasm that had birthed it. Moderators had to lock threads, clarify data sources, re-upload corrected graphs. It became clear that transparency, while noble, comes with noise of its own. That tension between open discovery and controlled verification is now the heartbeat of modern astronomy. When everything is public, the boundary between revelation and rumor dissolves. But perhaps that's inevitable. The universe itself is democratic. It belongs to whoever can see it. Inside observatories, scientists debated how to balance the flood of amateur data with rigorous analysis. Some worried that false positives would drown real discoveries. Others argued that human intuition, even if messy, had just proven its worth. A consensus began to form: collaboration, not replacement. Let the public cast the net wide. Let professionals do the deep dive. The strategy paid off. One amateur team in Poland detected a faint variation in the comet S-tail alignment hours before professional arrays confirmed a magnetic interaction with the solar wind. Another, in Chile, noticed a brightness pulse that corresponded exactly with a water emission spike. These were not flukes, they were synergy. By the time large telescopes caught up, the comet had become a community. People who had never spoken now shared spreadsheets of magnitude measurements, timing notes, and spectral overlays. Language barriers melted under shared awe. Somewhere between the noise and the math, the boundary between scientist and citizen blurred into something new, a network of wonder. Still, the professionals couldn't ignore the cost. With every open data set came hundreds of wild interpretations. The signal-to-noise ratio, both scientific and social, began to mirror the universe itself. Vast, beautiful, full of static. That's the paradox of discovery. The more eyes you invite, the harder it becomes to agree on what they see. Even so, something profound had changed. 3. I saw. Atlas wasn't just an object of study anymore. It was a shared experience. When the comet's activity peaked, online observatories hosted live streams that drew millions of viewers. Comments scrolled faster than the stars. Greetings from Pakistan, from Brazil, from Japan. People trading local midnight for a glimpse of alien ice. For a moment, the planet itself became a telescope. Every eye turned upward. Later, when the comet began to fade, many of those same viewers described a sense of loss, the quiet ache that follows wonder. One user wrote simply, "It feels like the universe waved back." And maybe it did, Because in that convergence of amateurs, professionals, and dreamers all staring at the same faint blur, something new had formed. A mirror. 3-Eye Atlas showed us not just chemistry, but cooperation. Not just mystery, but connection. A comet from another star had reminded humanity that curiosity too can be interstellar. As its green halo dimmed and its path curved away from the sun, the shared observation effort slowly dissolved back into daily life. But the data remained. Terabytes of light, carefully archived, waiting for future eyes. Perhaps one day another visitor will arrive, and somewhere in those records, someone will recognize the same patterns, the same anomalies, the same heartbeat. When that day comes, maybe the first alert won't come from a machine at all. Maybe it'll come from a quiet room, a glowing screen, and a single human whisper. There's something alive in that image. After the storm of discovery, after the media flares and the conference calls, came silence, the kind that sits heavy in observatories once the headlines fade. Atlas was still there, still glowing faintly in the black, but its behavior had changed. The violent outbursts of earlier months had subsided into a strange calm. The comet rotated steadily, exhaling only thin, rhythmic streams of vapor. Its coma dimmed to half its previous brightness, yet the ultraviolet readings refused to flatten. Something unseen was still happening beneath the quiet. Astronomers call it the plateau phase, the moment when activity stabilizes before final decline. But this plateau felt alive, like the breath before a sentence. Spectral analysis during those weeks uncovered a peculiar oscillation. Every few days the cyanide line deepened slightly, then weakened again. The amplitude was too regular for noise. Some hypothesized that sunlight modulated through the comet's spin axis, illuminating hidden vents in a repeating pattern. Others wondered whether chemical reactions inside the nucleus were self-sustaining. Slow burn cycles, driven by trapped energy rather than surface heat. That idea was radical, but not impossible. When cosmic rays penetrate ice, they split molecules, creating reactive fragments, radicals that can recombine later when warmed. If those reactions occur in waves, the comet might literally breathe chemically, releasing gas without external trigger. It would be the first observed case of a self-modulating comet, not alive but certainly not inert. Such speculation walked a fine line between physics and poetry. Still, it explained the data better than anything else. The silence, it turned out, wasn't absence. It was rhythm. During this lull, many scientists turned to modeling. Computer simulations tried to reconstruct the comet's internal structure from its behavior. The best fit suggested a honeycomb interior, a labyrinth of voids connected by narrow throats, like the lungs of a frozen creature. Each cavity stored different volatiles. As one emptied, heat from chemical reactions migrated through the porous rock, igniting the next. That cascading release could sustain periodic outgassing even far from the sun. In a way, Atlas had become its own engine. The irony was not lost on anyone. The object that once defied all expectations of activity was now teaching us that even chaos has pattern, that silence itself might be structured. Meanwhile, radio astronomers began listening. Using deep space arrays originally built to study pulsars, they turned their antennas toward the coordinates of the comet, hoping to catch non-thermal emissions, the subtle hiss of electrons spiraling along magnetic fields. They found something faint but consistent, low-frequency radio noise fluctuating in sync with the 19-hour rotation period. The signal was weak, buried under cosmic background, but the timing was uncanny. Was it simply solar wind interacting with ionized gas? Most likely, and yet, the pattern's regularity sparked curiosity. Natural processes can create rhythm, but rarely precision. One team described it as quasi-harmonic, meaning it repeated with almost musical structure. That word, musical, made headlines again, Can suddenly the internet revive the same question it always asks when faced with mystery? Could it be artificial? Scientists sighed. There was no reason to think so. But there's something irresistible about a pattern emerging from chaos. Humans have always mistaken order for intention. We see faces in clouds, voices in static, purpose in stars. And perhaps that instinct isn't folly. It's empathy projected onto the cosmos. Regardless of origin, the radio signal gave researchers a new window into the comet's environment. By mapping how the frequencies changed with solar wind pressure, they inferred the size of the ion tail, millions of kilometers long, a ribbon of charged gas so diffuse it could envelop entire planets without notice. That tail wasn't uniform. It rippled like fabric. Some nights, under favorable angles, Earth-based telescopes captured faint polarization, a kind of shimmering twist in the light that hinted at magnetic turbulence moving through the plasma. It looked, for lack of a better term, like whispering smoke. For months, Teotihuacan Atlas held that steady rhythm, a slow, dignified exhale as it drifted outward. Astronomers expected its brightness to fade quickly once it passed beyond Mars's orbit. Instead, it lingered. The coma remained luminous long past predictions. Some theorized that microfractures exposed deeper ices resistant to sunlight's retreat. Others proposed the comet's spin had tilted, giving new surfaces intermittent warmth. Either way, it was as if the object refused to go quietly. During that period, a few astrophysicists began to think less like observers and more like archivists. They realized this silence, this quiet persistence, might be their final chance to extract meaning. Every molecule leaving the comet was a word in a language soon to disappear. So they built databases, matching spectra to temperatures, building a library of alien chemistry. Thousands of lines of light, catalogued by frequency, each one a frozen echo of another star's history. One researcher described it beautifully. We're listening to a conversation that ended billions of years ago. But space is kind enough to replay the recording. It's easy to forget how much patience science requires. For every flash of discovery, there are months of staring into near emptiness, tuning instruments waiting for faint whispers to rise above static. The silence between signals is where understanding grows, not from noise but from its absence. Yet that calm would not last. Because deep in the comet's core, pressures were building again. In late-season images, faint streaks appeared, not from tail fluctuations, but from debris. Tiny fragments had begun to separate, drifting along the orbit like breadcrumbs. It was the first hint that Three Eyes Atlas was starting to come apart. At first, no one wanted to believe it. Fragmentation meant the end, but the evidence grew undeniable. High-resolution images from Hubble showed elongation, the nucleus stretched slightly, like clay under tension. Then one night it split. Two distinct cores emerged, trailing one another in slow motion, wrapped in the same ghostly coma. By the next observation, one had already dimmed, evaporated into mist. The silence was over. The comet that refused to fade had begun its final act. After the storm of discovery, after the media flares and the conference calls, came silence, the kind that sits heavy in observatories once the headlines fade. So Atlas was still there, still glowing faintly in the black, but its behavior had changed. The violent outbursts of earlier months had subsided into a strange calm. The comet rotated steadily, exhaling only thin, rhythmic streams of vapor. Its coma dimmed to half its previous brightness, yet the ultraviolet readings refused to flatten. Something unseen was still happening beneath the quiet. Astronomers call it the plateau phase, the moment when activity stabilizes before final decline. But this plateau felt alive, like the breath before a sentence. Spectral analysis during those weeks uncovered a peculiar oscillation. Every few days, the cyanide line deepened slightly, then weakened again. The amplitude was too regular for noise. Some hypothesized that sunlight modulated through the comet's spin axis, illuminating hidden vents in a repeating pattern. Others wondered whether chemical reactions inside the nucleus were self-sustaining, slow burn cycles driven by trapped energy rather than surface heat. That idea was radical, but not impossible. When cosmic rays penetrate ice, they split molecules, creating reactive fragments, radicals that can recombine later when warmed. If those reactions occur in waves, the comet might literally breathe chemically, releasing gas without external trigger. It would be the first observed case of a self-modulating comet. Not alive, but certainly not inert. Such speculation walked a fine line between physics and poetry. Still, it explained the data better than anything else. The silence, it turned out, wasn't absence. It was rhythm. During this lull, many scientists turned to modeling. Computer simulations tried to reconstruct the comet's internal structure from its behavior. The best fit suggested a honeycomb interior, a labyrinth of voids connected by narrow throats, like the lungs of a frozen creature. Each cavity stored different volatiles. As one emptied, heat from chemical reactions migrated through the porous rock, igniting the next. That cascading release could sustain periodic outgassing, even far from the sun. In a way, Cyathulus had become its own engine. The irony was not lost on anyone. The object that once defied all expectations of activity was now teaching us that even chaos has pattern, that silence itself might be structured. Meanwhile, radio astronomers began listening. Using deep space arrays originally built to study pulsars, they turned their antennas toward the coordinates of the comet, hoping to catch non-thermal emissions, the subtle hiss of electrons spiraling along magnetic fields. They found something faint but consistent, low-frequency radio noise fluctuating in sync with the 19-hour rotation period. The signal was weak, buried under cosmic background, but the timing was uncanny. Was it simply solar wind interacting with ionized gas? Most likely, and yet, the pattern's regularity sparked curiosity. Natural processes can create rhythm but rarely precision. One team described it as quasi-harmonic, meaning it repeated with almost musical structure. That word, musical, made headlines again, and suddenly the internet revived the same question it always asks when faced with mystery. Could it be artificial? Scientists sighed. There was no reason to think so. But there's something irresistible about a pattern emerging from chaos. Humans have always mistaken order for intention. We see faces in clouds, voices in static, purpose in stars. And perhaps that instinct isn't folly. It's empathy projected onto the cosmos. Regardless of origin, the radio signal gave researchers a new window into the comet's environment. By mapping how the frequencies changed with solar wind pressure, they inferred the size of the ion tail, millions of kilometers long, a ribbon of charged gas so diffuse it could envelop entire planets without notice. That tail wasn't uniform. It rippled like fabric. Some nights, under favorable angles, Earth-based telescopes captured faint polarization, a kind of shimmering twist in the light that hinted at magnetic turbulence moving through the plasma. It looked, for lack of a better term, like whispering smoke. For months, Cyathulus held that steady rhythm, a slow, dignified exhale as it drifted outward. Astronomers expected its brightness to fade quickly once it passed beyond Mars's orbit. Instead, it lingered. The coma remained luminous long past predictions. Some theorized that microfractures exposed deeper ices resistant to sunlight's retreat. Others proposed the comet's spin had tilted, giving new surfaces intermittent warmth. Either way, it was as if the object refused to go quietly. During that period, a few astrophysicists began to think less like observers and more like archivists. They realized this silence, this quiet persistence, might be their final chance to extract meaning. Every molecule leaving the comet was a word in a language soon to disappear. So they built databases, matching spectra to temperatures, building a library of alien chemistry. Thousands of lines of light, catalogued by frequency, each one a frozen echo of another star's history. One researcher described it beautifully. "We're listening to a conversation that ended billions of years ago, but space is kind enough to replay the recording. It's easy to forget how much patience science requires. For every flash of discovery, there are months of staring into near emptiness, tuning instruments waiting for faint whispers to rise above static. The silence between signals is where understanding grows, not from noise but from its absence. Yet that calm would not last. Because deep in the comet's core, pressures were building again. In late-season images, faint streaks appeared, not from tail fluctuations, but from debris. Tiny fragments had begun to separate, drifting along the orbit like breadcrumbs. It was the first hint that 3I Atlas was starting to come apart. At first, no one wanted to believe it. Fragmentation meant the end, but the evidence grew undeniable. High-resolution images from Hubble showed elongation. The nucleus stretched slightly, like clay under tension. Then one night it split. Two distinct cores emerged, trailing one another in slow motion, wrapped in the same ghostly coma. By the next observation, one had already dimmed, evaporated into mist. The silence was over. The comet that refused to fade had begun its final act. Long after the nucleus vanished from telescopes, its dust remained, a faint invisible wake stretching across millions of kilometers of interplanetary space. You couldn't see it, not even with long exposure. But it was there, a river of microscopic memories flowing through the sunlight. Each particle carried a fingerprint, the isotopic ratios of hydrogen, carbon, nitrogen, and oxygen from a star that no longer shines. To scientists, these weren't just specks. They were time capsules, each one preserving conditions from an era before the sun existed. The strange thing about dust is that it doesn't die. It drifts, collides, merges, and becomes something else. Every atom in your body was once dust in a similar stream, the remains of forgotten worlds recycled by gravity into new beginnings. And so, in a quiet way, 3I Atlas had already begun to join us. Its remnants were mixing with ours. Weeks after the breakup, the European Space Agency's solar observatories noticed subtle changes in the solar wind, faint upticks in ionized nickel and carbon compounds, appearing right along the trajectory of the fading comet. It was a ghost signature, like the perfume of something long gone. The solar wind was swallowing the comet's remains, scattering them through the heliosphere. By modeling those flows, researchers traced where the debris would travel. Within a year, the stream would cross Earth's orbit, not enough to form a visible meteor shower, but enough to pepper the upper atmosphere with particles from another star. That thought alone was staggering. Alien dust entering our sky, burning silently, unnoticed by the billions who would never know it happened. Somewhere, over deserts or oceans, those grains would meet air at 60 kilometers per second. They'd flash for a millisecond, a microscopic streak of green or blue, then vaporize. The atoms would mix with nitrogen, oxygen, and trace gases, becoming part of Earth's air. That's how intimacy works in the cosmos, invisibly, inevitably. Every breath we take already contains the ashes of ancient stars. Soon it would include whispers from 3I Atlas as well. For planetary scientists, this was more than poetry. The dust composition offered a clue to a long-standing question: how universal is the recipe for worlds? If interstellar debris like this carries familiar chemistry, it suggests that planets, and maybe even biology, follow similar blueprints everywhere. But if the ratios differ, if these grains hold exotic isotopes or unheard-of minerals, then perhaps the Milky Way's diversity is deeper than we dare imagine. To test that, teams prepared stratospheric collectors, fragile foils mounted on high-altitude balloons that skim the upper atmosphere, gathering whatever the cosmos sheds. Most of what they catch is terrestrial: volcanic ash, industrial soot, meteor remnants from our own solar system. But buried among those once in a while is something unrecognizable, a grain whose isotopic balance screams elsewhere. A decade from now, Perhaps one such grain will be traced back to this comet, its nickel lines matching the spectra we recorded today. That would make it the first physical fragment of another star system ever touched by human hands. But that verification will take years, maybe lifetimes. Science moves on timescales as slow and patient as dust. Meanwhile, the light curves faded to nothing. The comet was gone. But its trajectory continued to fascinate. By projecting its path forward, astronomers calculated where it would go next. Outward past Jupiter's orbit, then through the Kuiper belt, and finally beyond the heliopause, back into interstellar space. It would rejoin the same galactic tide that once delivered it to us. Its velocity, 32 kilometers per second relative to the Sun, guaranteed escape. Even gravity couldn't recall it. What's humbling is that most of it will persist. The fragments too small to see will travel for billions of years. In that time, they might pass other systems, other stars, other watchers. Somewhere centuries from now, another civilization might detect faint cyanide lines in their telescopes and wonder about a comet entering their sky. They'll give it a name, measure its orbit, find its strange abundance of nickel, and perhaps realize it came from somewhere else, from a yellow star in a spiral arm, half a galaxy away. If they do, they'll be watching our dust. That's the quiet symmetry of the cosmos. Everything becomes someone else's discovery eventually. For a while, researchers tried to trace whether Three-Eyed Atlas left any gravitational echoes. Perturbations on nearby asteroids, small wobbles in the orbits of known comets. Nothing substantial appeared. Its mass was too small, its stay too brief. It passed through the solar system like a rumor, leaving only curiosity in its wake. But rumors can outlive facts. For scientists, its data archive became a new benchmark, the reference against which all future interstellar objects will be compared. Months later, when the raw observations were cleaned and compiled, one curious pattern emerged. In every spectral dataset, there was an unexplained faint baseline noise, a soft, irregular flicker that repeated across multiple instruments. It wasn't telemetry, nor cosmic rays, nor calibration error. The signal was correlated faintly with solar wind fluctuations, almost as if the dust itself was interacting electromagnetically in ways not yet understood. The effect was tiny but real. It hinted that Three-Eyed Atlas's remnants might still be responding to the Sun long after the nucleus had gone. Some called it poetic coincidence. Others wondered if the dust, ionized and delicate, had become part of the solar wind's fabric, a temporary bridge between two systems. Either way, it added one final note to the object's strange symphony, a fading echo that refused complete silence. For the people who'd followed it from discovery to dissolution, the end felt strangely personal. They had watched it breathe, fracture, and vanish. Now all that remained were files, terabytes of numbers, graphs, and images. Yet those pixels held something living, the trace of an encounter between two suns separated by light years. In that sense, the dust did remember. It remembered the heat of another star, the chill of the void the moment it met ours. And perhaps one day it will carry those memories forward to somewhere new. We tend to think of discovery as finding something, but sometimes it's realizing what has already found us. Three-Eyed Atlas didn't come to be understood. It came to remind us that every atom is a traveler, that everything we know once belonged somewhere else. If you go outside tonight and breathe deeply, the air tastes the same as it always has. But invisibly, silently, a few of those molecules might once have belonged to a comet that crossed galaxies to meet you. And that makes every breath a kind of conversation. When the images faded and the comet slipped into data archives, what remained was mathematics, rows of numbers, curves, ratios, noise. For most people, it looked like the aftertaste of wonder, something dry, stripped of mystery. But for the scientists who had followed Three-Eyed Atlas, those equations were alive. They were the echo of everything the sky had whispered. You could see its entire life written there, The light curve traced its pulse, a wave rising, peaking, breaking, then flattening into silence. Spectral lines mapped its breath, the rhythm of water, carbon dioxide, cyanide, nickel, oxygen. Even its death had an equation, an exponential decay describing how brightness faded after the nucleus broke apart. Some found comfort in that precision. Others found it almost cruel, because no formula, no matter how elegant, could recreate the feeling of watching that pale green coma shimmer in real time. Yet the numbers were all we had left, a language the universe speaks fluently even when we don't. Mathematics is a strange kind of poetry. It doesn't describe beauty, it creates it. A curve fitting perfectly through chaos is a kind of art, a portrait of order drawn on the canvas of randomness. And 3 Amanus Atlas, in its defiance of expectation, forced new art into being. Equations had to stretch, assumptions had to break. Every anomaly became a challenge. Why did its water production peak when moving away from the sun? Why did nickel persist without iron? Why did the cyanide emission oscillate in time with its rotation, as if synchronized? Each answer led to deeper questions, each question reshaping how we imagine the architecture of other star systems. To decode those patterns, researchers built models of chemical kinetics under alien conditions. They simulated reactions inside amorphous ice, traced diffusion rates of carbon compounds through microfractures, mapped the radiation shielding of cosmic dust. In digital space, they rebuilt the comet, not as an image, but as an equation of itself, a mathematical phantom that breathed the same rhythm its real counterpart once did. Those models revealed something profound. Even in the most exotic scenarios, ancient thick disk chemistry, altered isotopic ratios, low metallicity conditions, the patterns still converged toward familiar laws. Energy conservation, sublimation thresholds, radiation dynamics, all obeyed the same physics we know. The comet's strangeness, in the end, wasn't a violation of nature but a reinterpretation. The universe had simply used the same rules to write a different poem. That realization became a quiet comfort to those who feared science might lose its magic. Because if wonder can be measured and still feel infinite, then perhaps we never lose it at all. We just learn new ways to listen. In one particularly haunting simulation, a research group reconstructed the comet's final days in 3 dimensions. They modeled the sunlight filtering through the fragmented dust, the faint jets of gas twisting as fragments rotated apart. The result wasn't cinematic, it was almost tender. They called it the slow collapse of an idea. The name fit. Because 3I Atlas had become more than an object, it was a metaphor for curiosity itself. Bright, fragile, self-consuming, always leaving questions in its wake. The data didn't end at chemistry. Some physicists examined the orbital mechanics in detail, noting subtle deviations that couldn't be explained by outgassing alone. These were small, a few meters per second of acceleration here, a fraction of a degree there, but consistent. They called it non-gravitational motion, the same phrase once whispered around Oumuamua. Most likely it was jet asymmetry, the uneven push of vapor jets acting like tiny thrusters. But still, some allowed themselves to wonder, what if there was something more subtle, a microphysical effect we hadn't yet described? Radiation pressure acting on exotic dust grains? Electromagnetic coupling with the solar wind? Such questions keep astrophysics alive. They remind us that every mystery is just the boundary of our current vocabulary. As data analysis deepened, one pattern emerged that no one expected. When plotting the ratio of nickel emission to cyanide over time, a curious phase shift appeared, a lag of precisely 57 minutes between the peaks. At first it looked like error, but after repeated verification the lag persisted. No current model could explain it cleanly. One theory suggested alternating vent locations on opposite sides of the rotating nucleus. Another proposed layered chemistry, with nickel locked in deeper ices that took exactly 1 rotation lag to activate after cyanide release. Whatever the reason, the number remained fixed, as if engraved into the comet's timing, an alien metronome ticking across light years. A poet might say that the comet kept time with its own heartbeat. A scientist would call it thermal phase lag. Both would be right. The 57-minute shift became a kind of signature. Years later, when future missions detect new interstellar visitors, that ratio will be the first thing they check. If it appears again, we'll know we're seeing a relative, a sibling from the same long-lost nursery. If not, we'll know 3A. Atlas was unique, a solo note in the galaxy's long song. Beyond the physics, though, something human remained in the data. Many of the researchers who worked on the project found themselves dreaming about it, literally dreaming. They described images of green light in darkness, of particles drifting endlessly, of equations glowing like constellations. For them, science had blurred into something spiritual. The realization that understanding the universe doesn't make it smaller, it makes it intimate. Because when you can describe the heartbeat of a comet in minutes, when you can trace its chemistry atom by atom, when you can calculate the precise second it began to die, you realize how much of yourself is built from the same mathematics. The same physics that governed 3I Atlas governs you. The sublimation of energy, the fracture under pressure, the beauty in equilibrium. In that sense, studying it was like studying our own reflection, a cosmic self-portrait written in hydrogen and light. When the final reports were published, they were dense, technical, cautious. The word mystery appeared nowhere, but between the lines you could feel it. Every graph was an act of reverence. Every data point was a confession of awe. Because behind every equation lies the same truth. We count things not to control them, but to remember them. And 3. Atlas was worth remembering. There are moments in science when the observation feels mutual. When you point instruments toward the sky and feel somehow that the sky is aware of it. It's illusion, of course, but a powerful one. During the final months of studying 3I Atlas, many astronomers described that feeling, as though while they measured it, the comet was measuring them too. It wasn't mysticism. It was perspective. To study something so old, so alien, is to be seen by time itself. Every photon bouncing from that icy surface carried an image of us back into the dark, encoded forever in the light it reflected. Long after the comet has left, those photons will continue outward, carrying the memory of a small blue planet that once looked up and wondered. In a real physical sense, we are now part of that object's journey. We are embedded in its reflection. When future civilizations in some distant system detect a faint echo of sunlight bouncing off 3I Atlas's dust, they'll see Earth in it, a spectral fingerprint of our own sun, our own light. Observation, it turns out, is participation. That idea fascinated the scientists who spent years tracking it. They began to talk about reciprocity, that strange philosophical reciprocity between observer and observed. We measure the universe, yes, but in the act of measuring we also change ourselves. We learn to see differently, to think beyond human time. By the end of the mission, many of them had become philosophers in lab coats. In the quiet after the comet's disappearance, one research team compiled what they called the Reflection Archive, a collection not just of data, but of personal notes, logs, midnight messages, stray thoughts written during observation shifts. It read less like a paper and more like a diary of wonder. One entry, scrawled between calibration notes, said simply, "When I look at it, I feel like it's looking back." Another wrote, "If atoms can travel from one star to another, maybe questions can too." That sentiment spread quietly through the scientific community, a reminder that curiosity itself is a form of kinship. Because in trying to understand 3I Atlas, we glimpsed how the universe understands itself. Each discovery was a mirror, each mystery a reflection of our limits. Meanwhile, instruments still watched the space it had vacated, searching for residual trails. Some data analysts found faint photometric irregularities in the region, small fluctuations that could be leftover dust clouds. Others thought they saw nothing at all. But everyone agreed on one thing. The comet had changed the way they looked at the night sky. Before, the darkness had seemed indifferent. After, it felt inhabited, not by life necessarily, but by meaning. The philosophical discussions turned practical when new telescopes came online. Designs for future survey systems included algorithms explicitly tuned to catch objects like 3i Atlas sooner. Lessons learned from its trajectory refined the way we search for interstellar wanderers. Humanity, it seemed, had learned how to listen a little better. That was its real legacy, sensitivity. Not just in instruments, but in perception. During one conference months later, a veteran astronomer summarized it perfectly. We always think discovery means seeing more. Sometimes it means seeing differently. The audience fell silent. They all understood what she meant, because 3i Atlas had shown them that mystery isn't a gap in knowledge, it's a feature of it. The universe doesn't hide its secrets out of malice. It reveals them slowly in proportion to our patience. Outside the world of observatories, the comet lingered in culture. Poets wrote about it. Musicians sampled recordings of its radio emissions. Digital artists recreated its spectral colors in soundscapes. One installation in a museum in Berlin turned its light curve into a visual symphony, each dip and rise a musical note. Visitors stood surrounded by waves of green and white, listening to the rhythm of a dying comet turned into melody. Even people who had never seen it through a telescope could feel what it meant. That's the mark of a true discovery, when it transcends its own data. Somewhere in the midst of all this, a new thought began to circulate. Maybe the cosmos doesn't just exist out there. Maybe it's relational, something that only becomes real when we notice it. A photon doesn't become meaningful until it hits a detector. A mystery doesn't become beautiful until someone wonders about it. In that sense, 3i Atlas was a collaboration between stars and consciousness. It existed billions of years before us, but only found meaning once we looked. When you think about it that way, every discovery becomes a conversation. The universe speaks through light, through gravity, through the geometry of motion. And we respond with curiosity, with instruments, with awe. That dialogue has no end. We are both questions and answers, echoing each other across time. And maybe that's why 3i Atlas felt different from any comet before it. It wasn't just data, it was an encounter. The first time Earth truly listened to another system and heard something whisper back. In the final report, buried in an appendix, one sentence stood out among the tables and figures. The object's persistence of activity beyond thermal expectation suggests a non-trivial interaction between internal chemistry and external environment. That's how science says, we don't fully understand it. But between the lines, another meaning shone through, that maybe understanding isn't the point. Maybe wonder is enough. And so the story of 3i Atlas ends not with a conclusion, but with a question, one that looks back at us through the dark. If a fragment of another star can reach us across light years, what else is already on its way? Light is a peculiar form of memory. It travels endlessly, carrying the imprint of whatever created it. A record written not on paper or film, but in frequency and phase. Every photon that touched 3i Atlas during its brief visit now races outward through space, spreading the news that for one heartbeat of cosmic time, two suns once shared the same sky. Those photons will travel forever. In 10,000 years, they'll pass the orbit of another star. In 1,000,000, they'll cross a spiral arm. Long after every observatory on Earth has crumbled, the light that left our telescopes will still be moving, a message without an address. Perhaps one day someone will catch it, some civilization orbiting a blue-white star, building their own catalogue of wanderers. and wonder what strange system sent a glimmer of green and nickel-bright spectra drifting through the dark. They will reconstruct our sun from that faint reflection. They will know briefly that we existed. In that sense, every observation is two-way. When we study the universe, we leave our signature upon it. The act of seeing writes both directions. And so 3 Akaj Atlas carries not only the chemistry of its birth star, but the reflection of ours, a mingling of stories that may never happen again. After its disintegration, astronomers turned their attention to that light. The final spectra, captured just before the comet faded beyond reach, contained something remarkable, a set of polarization curves that no one could explain. They hinted at microcrystals inside the dust, aligned in ways that implied structure, as though the comet's inner ice had grown under magnetic fields before being shattered. That detail might seem trivial, but to physicists it was astonishing. It meant the nursery of its origin wasn't just cold, it was magnetized, charged, turbulent. The kind of environment where new stars ignite. If those grains could speak, they would tell us about the birth of suns. Teams around the world raced to model it. They simulated the collapse of protostellar clouds, seeded with magnetic filaments and rotating gas, trying to reproduce the same polarization patterns. Most failed, but one simulation came close, one that assumed the comet had formed in the periphery of a binary system, where 2 stars danced close enough to twist magnetic fields into knots. That could explain everything. The nickel abundance, the magnetic alignment, even the fractured layering of ice. Atlas might have been born between 2 suns, in a place of perpetual tension, pulled by 2 gravities, frozen by 2 nights. If true, then what we witnessed was not the relic of one world, but the debris of 2 entwined fates, a story of duality, creation and destruction intertwined from birth. That realization rippled through the community like a quiet shiver. For months, papers explored the possibility of binary system chemistry, of how the dance of twin stars could forge comets unlike any we've known. But beyond the equations, the idea carried something human, the notion that even celestial bodies can be born in conflict, shaped by opposing forces that never fully let them go. The comet's light became a metaphor for that tension. When scientists reconstructed the brightness curve from its first detection to final fade, they noticed a symmetry. The rise and fall mirrored almost perfectly, like inhale and exhale. Mathematically, it was beautiful. Poetically, it was haunting. The universe, it seemed, had exhaled, and then gently gone still again. By now, the object was far beyond Mars, moving faster than any probe humanity has ever launched. It no longer produced gas or dust. It was dark, invisible except to radio telescopes that could sense the sunlight it reflected, a speck of coal against infinity. Yet from that faint reflection, researchers could still calculate its rotation, its wobble, its slow cooling. Even silence has data. Every few months, observatories reported updated coordinates. Each one placed it a little farther out. Its motion now dominated entirely by the gravity of the galaxy itself. Soon, even that pull would become negligible, and 3i Atlas would drift among the interstellar tides once more. It was returning home, or at least to the same emptiness from which it came. Some scientists joked that the comet was carrying our fingerprints now. The radar pings we sent, the photons from our measurements, the tiny radiation pressure from our gaze, all had imparted the smallest possible push, changing its course by a fraction of a millimeter per second. Insignificant, yes, but not zero. We had nudged it ever so slightly, and that meant that humanity too had entered the ledger of its motion. When historians of science look back, they'll see this era as the moment we began to treat interstellar objects not as curiosities, but as correspondence, letters between stars. Each one that arrives will carry chemistry, memory, maybe even fragments of ancient magnetism. Each will rewrite our understanding of what planetary system means. Atlas was the first letter we managed to open properly. Its light, faint, fragmented, scattered, is still being analyzed today. Deep in data archives, graduate students measure ratios, write papers, and build careers on details that once flashed across a telescope for seconds. For them, the comet is no myth. It's homework. Yet even in their dry figures there is reverence, because every graph of its light is also a graph of time. Each photon is an artifact of coincidence, the intersection of chance and curiosity. One of those students once wrote in a forum post, "Sometimes I think light remembers us better than we remember ourselves." It became a quiet motto among the team, and maybe that's the comet's last lesson, that memory doesn't need minds. The universe remembers through motion, through heat, through the persistence of light. Every ray that left that dying comet is still carrying its story outward, expanding into eternity. Every equation, every observation, every line of code we wrote to understand it, adds our own light to that wavefront. In the end, memory and illumination are the same thing. The cosmos doesn't archive events in libraries. It keeps them as radiation. Somewhere between stars, the memory of that green glow still travels. And inside it, perhaps the reflection of the humans who once paused, looked up and whispered, "What is that?" If you could follow that photon forever, you'd never find an end. Only more darkness to cross, more silence to illuminate. That's the closest thing to immortality the universe offers, to have existed brightly enough that your light keeps going. And so, as my atlas drifts back into the unseen, we are left with echoes, data, ideas, wonder, and the understanding that nothing observed is ever truly gone. It just keeps moving one beam at a time. By the time 3i Atlas left the inner solar system behind, it had already done something extraordinary. It had changed the way we listen to the universe. Before it arrived, interstellar objects were theory, footnotes, statistical ghosts in equations about galactic drift. After it left, they were real, solid, measurable, and hauntingly familiar. What remained wasn't a body of ice and dust. What remained was awareness. Somewhere between the first detection and the last trace of light, humanity learned that we are not isolated within our own star's debris. We are part of a conversation stretching across the galaxy. The object itself was gone now, too faint for any telescope, too distant even for radar. Yet in the laboratories of Earth, its story continued. Samples of simulated interstellar ice sublimated under controlled light, mimicking the comet's chemistry. Computers ran models for days, testing how nickel and carbon dioxide might coexist without iron, how cyanide could survive radiation older than memory. Each discovery led not to closure, but to invitation. Each answer felt like a door opening into a darker hallway. The strange part is how quiet that curiosity feels once the object is gone. There is no explosion, no final signal, just silence filled with possibility. The scientists who studied it often described withdrawal symptoms, the way deep-sea divers talk about surfacing too fast. You spend years peering into a piece of infinity, then suddenly the data stream stops. The night becomes just night again, but silence is deceptive, because even without the comet, its absence began to speak. Without realizing it, researchers started hearing similar spectral fingerprints in other data, tiny hints of nickel excess, slight cyanide irregularities, faint CO2 dominance. None were confirmed interstellar visitors yet, but all were potential. It was as if the universe, having sent one messenger, decided to send more. The search widened. Telescopes once built for asteroid defense were reprogrammed to watch the deep sky for fast-moving hyperbolic objects. New algorithms learned to recognize the specific rhythm of outsiders. The next time something crossed our solar boundary, we'd be ready. And in that readiness lay something beautiful, hope disguised as procedure. Meanwhile, in a remote radio observatory in Chile, a small anomaly appeared in background noise, a repeating oscillation near the same frequency, once observed from 3i Atlas's plasma tail. It wasn't identical, just eerily similar. The pattern repeated every few hours, then faded. Maybe it was nothing. Maybe it was everything. No one could say for sure, and perhaps no one should, because mystery, left unresolved, becomes the engine of discovery. That's the quiet gift the comet left us, the ability to live with unanswerable questions. The idea that the universe might listen back began as metaphor, but in subtle ways, it's also literal. Every radar ping, every photon reflected, every radio wave we send bounces outward, touching worlds we'll never know. The galaxy, indifferent yet inclusive, keeps all of it. Our transmissions are fossils in motion, light-speed diaries expanding through eternity. And somewhere among those diaries now travels the record of our encounter with 3I Atlas, our measurements, our astonishment, our questions encoded in data. We didn't just observe it. We inscribed ourselves into its trajectory. That's how observation works. It binds both sides of the lens. If you imagine the Milky Way not as a place but as a network of stories, then each star system is a voice, each comet a messenger, each civilization a temporary translator of the same cosmic language. Taihatla spoke briefly, in chemical syllables we barely understood. We answered with mathematics, light and wonder. And then the voice faded, but not before teaching us the grammar of awe. Perhaps that's what science is at its core, not the pursuit of certainty, but the rehearsal of amazement. Years later, the archives remain open. Students still download the raw frames, still marvel at the symmetry of its death, still whisper the name as if it were a myth. For them it is, but myths are just truths we tell in poetic time. Outside, the universe continues its quiet breathing. Somewhere beyond the heliopause, the fragments of 3I Atlas drift through the interstellar medium, cooling toward absolute zero. They are dark now, no reflections, no emissions. Yet each carries within it the memory of warmth, the echo of two stars that once shared their light. And somewhere else, perhaps billions of kilometers away, a new comet is beginning its journey toward us, invisible for now, following a trajectory written long before humans had eyes to see. It may arrive tomorrow or in 1,000 years. Either way, when it comes, we'll be watching. We'll have learned to listen differently, to notice the faintest flicker, the softest deviation, the subtle pulse that says, I am not from here, because of 3I Atlas. We know what that whisper sounds like. The universe doesn't shout its revelations. It hums them quietly, endlessly, until someone finally pauses long enough to hear. And maybe that's all 3I Atlas ever wanted, to be heard once by a world ready to listen. So the story closes not with discovery, but with awareness. That everything we see, every photon, every fragment, every question, is part of the same great conversation. That wonder is not a feeling but a responsibility. To keep listening, even when the voice fades. If you stand under a clear night sky and wait long enough, you might notice it. The faint hiss of air, the background hum of the world turning, the low static of existence itself. That's not silence. That's the universe remembering. And somewhere in that hum, if you listen carefully, you can almost hear a voice from another star whispering back, I was here. And so were you.